So now we'll welcome Professor Lucia, is a professor at North Carolina State University, internationally recognized for his work in green chemistry, biomaterials, and sustainable systems. Beyond his scientific contributions, he leads interdisciplinary research in systems thinking and social cooperativity, bridging the natural sciences with human and societal development. His perspective invites us to see human interaction not as isolated behavior, but as part of a dynamic, interconnected system. Please join me in welcoming his presentation called Theory of Human Interactions, an Entropic and Cooperative Regulative Framework.
Thank you, Johnny. If anyone doesn't hear me well, please feel free to speak up.
You sound great.
Can you hear me okay?
Yeah, I said okay. You sound great.
Okay, great. Thank you. So what I want to do today, I first want to thank the speakers and the organizers for this wonderful framework that we have. I'm particularly happy to follow Dr. Alexandrova for her wonderful discussion that sort of leads into this. So this is a little bit following what she proposed. So there's a lot of interesting sort of elements that she described that follow this. And so today I want to share with you what it looks like, what possibly the human interactions are for regard to our overall, humanity and structures. So first, I lead off with entropy, the idea that there is a physical quantity that gives us an understanding of what we are fighting, right? Because entropy, for physicists at least, and a lot of scientists, it encompasses disorder, right? And you see here the idea of a measure of disorder of microstates. As Dr. Alexandrova said, you have these systems like in plasma where electrons can behave in certain ways to either create a uniformity or disruption. And generally, when physicists look at entropy, they say, it's a state of disorder the universe is going to. But what I want to do today is show how this could potentially be in our favor, because again, as she showed so eloquently, this death equality to life is really what I'm trying to do here with entropy. So with regard to human society, if we look at, for example, the idea of disorder, right? This is what all of us in a way kind of reflect, the idea of this system where there's just so much, horror, there's just a riot-like disorder, right? But in a low entropy state where you're essentially starting to piece things together, this idea of order starts to really come through, right? The idea that everything is harmonized. But what I want to show you essentially is that there is an order in this disorder if we do it correct, if we look at it correctly, and if the environment essentially is the catalyst for this change. So, for example, my thesis is that human entropy, this idea that I just showed you in the past slide, it can be beneficial once we understand the concept of positive human interactions within a framework, right? A regulative framework, as I say in the title. Why does this matter? Well, because today, as you know, as we see, there's a lot of societal complexity. There's a lot of issues. There's a lot of problems that we have that could be categorized as fragmentation, as polarization, information overload. There's a lot of issues that we face that can stymie this whole idea of order, right? So what do we do? So for us, what we have to think about is, how do we take advantage of disorder? How do we make it constructive? How do we convert death into life, as Dr. Alexandrova said? And, the differences that we have within our society, can we find strength? Can we find them? So today, what I hope to show you and sort of help you guide your thinking is that this idea of entropy I equate in a human society to diversity, uncertainty. It's kind of a disorder. Like, hey, it's not uniform. It's not, part of a very cohesive, at least intuitively, whole. We need an environment, a cooperative scaffolding, and what that means is how does the environment, what it finds itself in, entropy, human entropy, lead to adaptive order? If we perceive positive interaction, right? If, like Dr. Alexandrova said, if we start to change our thinking in a way that we see a system-wide objectification, let's look at differences through the lens of connection. Seeing that the synergy of differentiations can lead to a strength, right? And that can lead to resilient trust, to recovery from issues that normally would otherwise shock us, and we can be whole. We don't all have to find a unity through identification, with each other in the sense that we're all monolithic. No, we can be ourselves and still adapt to an environment that is beautiful, right? So entropy is not the problem. This is my claim. It's lack of cooperation. It's cooperativity. How do we as human beings start to believe that cooperation is the key feature that we need to embrace? And if we can do this, what comes is amazing. Trust. We start to realize that we're not at odds. We're not enemies. We start to adapt. We start to see each other's features as a strength, because each one can, in a society, in a colony, in an animal environment, can, do their work. And this all brings us into a cohesive framework. In general, in nature, as was said in this IHOOD International Conference, entropy has to happen. It's just the nature of our universe. As a plant grows, it starts to bridge its environment with its roots. And this is a form of entropy where you have this kind of disorder. But what's beautiful is that in this disorder, there's an amazing and unique order. And this diversity that you see, because its roots are everywhere, it grants us a sort of opportunity to scaffold, to bring together our differences and our diversity of views and our behavioral uncertainties. This is what we really want to see, because again, we can't make everything homogeneous. So in terms of positive and negative, we see the opportunity to innovate, to take a structure that looks so fragmented and polarized and broken and make it innovatively work for us, so we can start perceiving things as in our favor. In my research, we see this in nano-confinement when we start to look at spaces, volumes that look so disorganized, that have no regularity. But what happens is that these places, these pores, they start to restrict movement. And then interactions happen, right? There's this constraint to the environment, the scaffold, and it causes things to work in a way that we would never have guessed. So, if I take the approach that we use science as a building block for understanding humans, we can equate humans to molecules. We see them as units, right? In terms of, the chemistry, these molecules have a certain identity and that they have a certain behavior in society. And we can say that the energy that we derive is from our, as Johnny said, our intention, our motivation. What is it that we want to do? And this would drive our movement, our motion, right? We can essentially start to engage in activity. And so this activity by default would lead to collisions, and these we would classify at the human level as interactions. In chemistry, they would be the cause of chemistry, of some changes in a system, right? And so when the environment allows for cooperativity, we can then build trust. right? We can build this bonding. We can build a stable relationships. We can start to enjoy the fruits of our interaction at a very high positive level. And activation energy is what in chemistry we generally consider to be a barrier, right? There's this wall, right? Like, oh, how do I get over it, right? But we can get over it, as I share in this next few slides. And again, thinking of it in a scientific sense, if we have high entropy and low cooperativity, because so we have a lot of disorder, but not cooperativity, where there's interactions. If we use those two variables, what it leads to is chaos. So high entropy and low cooperativity lead to chaos. If we have low entropy but high cooperativity, like I showed you in an earlier slide, we have rigidity. Everyone's the same. Nothing differentiates. There's just like up. Everything is monolithic. But if we have high entropy and high cooperativity, we can lead to adaptive order, where in places where you have differentiation, we have all kinds of diversity, we can lead to a system where everyone is working together. And this is based on the diversity of the people, of the molecules, the collisions, the interactions, and then the bonding, the trust. So our chemistry is very much, relevant in human society. And as a result of the equation, we get resilience, we get innovation, we get unity, right? And so the model is successful because we can take entropy and we can channel it through the environment for our benefit. And we can see this in organizations, in education, if we want to. Again, a lot of organizations and educational systems don't do this, but that's what we got to do. We've got to do this. So ultimately, my talk boils down to this. Entropy times cooperativity, like I showed you in that landscape set of slides, would lead to unity. So not E equals MC squared, but E times C equals U. And then ultimately, what I want you to take away from this is don't be afraid of entropy. Embrace it. And finally, in conclusion, according to IHOod, we'd like to recognize human interactions. They norm set them. Let's listen to everyone. Let's think about what everyone has to say. Curiosity-driven questions. Let's not humiliate. Let's embrace what people say. Working in small groups, this microstates, right? These cooperations, and then we federate. Then we sort of aggregate, right? The consensus or the divergency of opinions into something that brings it to the front. We bridge the cores, we seed the weak ties across all of these clusters, rotate members. We really try to bring everyone on board, right? That gives us, a unity. And then, we share information, we try to discuss, we try to verify what the signals are, and we bring them into a whole. And obviously, this is something that leads to gratitude, healing, and, transparency of commitments, and under what is termed as ritualized reciprocity. Beautiful. And I think that is it. Thank you very much for your attention, and I welcome any questions.
Okay, thanks, Professor. We have time for, I think, one question, one or two. So let's start with the Zoom. Ernest.
Thank you very much for the opportunity to ask the question. Thank you, Professor Lucian. Very, very impressive presentation. In the industry, typically I'm a quality engineer from the long career in the industry, but it's called communication, collaboration, and connection is actually tied in together. And the reason for this questions, you mentioned the entropy and you mentioned the cooperation, okay, multiplied together brings actually the best result. We know actually that the nature development is from still vegetative, animative to human level, and the human development is the connection on the top or highest level actually should bring actually to one global connection. Can you foresee any situation, like for example, like promoting the methodology of the round tables, okay, and to see how actually human collaboration in different circles. It was beautiful presentations regarding the family, regarding society, industry, science, the workplaces everywhere. How this can bring us to a better world, to fix or repair or to come to the point that actually the global leadership we realize and acknowledge that we are really able to make it. We are not able to make it through a round table and not through wars. Can you see what is your opinion regarding this one? Thank you.
Yeah, thank you, Ernest. Thank you. Beautiful. It's a beautiful question. I do believe that a round table is kind of a good analogy. It's like when I was a child, I loved the Arthurian fables of King Arthur and the knights, and the idea was that despite having a king, he would sit at a table equal with the folks that care about the kingdom. And I think this is a model that I've seen sort of, evolve in the microscopic states that I've studied. So we have matrices, we have scaffolds, we have these units that when, very small materials encounter them, essentially they work around these materials in a way to engender a very beautiful result, right? Meaning, like, if I put in a system of, say, dirt and water in these scaffolds, and I won't go into the chemistry but just general, these things organize, and they're chaotic. It's all chaotic, but they organize everything in a way that makes it beautifully whole. We get, a unity that is amazing. And at the macro level, like you're asking, Ernest, I think what has to happen is that we have to recognize our common goal, right? How do we as humans say, what do I want? What is it that I want to see happen, instead of, saying I know best, right? Like if there was one molecule that said this is the way to do it, the whole system would collapse, right? But, molecules behave according to the environment they're put in, and humans really don't unless the intention is there, right? Unless the directive, the object is there. And that's what I think is lacking in today's organizations and political governments is, what do we want that is really ultimately going to benefit all of us? I think, as an earlier speaker said, what are the benefits? How do we quantify them for everyone so that everyone can say, that's great, let's do it. And if we could get to that point where we objectify a common goal, I think we're very close to peace. I think war will be a thing of the past.
Okay, we have a lot of questions, and we're also out of time. But we're going to provide time for a couple more. But before that, I've just learned that when I have a stupid question, maybe others also have that question. So I just wanted to ask, first of all, did I understand correctly that entropy leads to connection?
Great question, John. Yes, I know that sounds ridiculous, but we actually wrote a paper on it, and we showed that it does. It does. I mean, at the molecular level, of course, but I think at the macro level, I wrote a proposal. Actually, this is for Ephraim to go to Israel to do this study in a more in-depth level, and I believe it does. Yeah, it's not a silly question. It's a great question.
Okay, even without the macro level, even on the microscopic level, could you just summarize real quick, like to a fifth grader, like how does that? Because I understood it to be the opposite.
Right. So what we've generally at the micro level, things are generally governed in sort of like organization by heat, temperature, energy. But what we found is that in spaces, really tiny spaces that would tend to create disorder, right? What we find is those spaces that, and again, this is at very small levels, right? We're talking like a billionth of a meter, right? So a billionth of a meter. What we find at that space is that things start to order. It's unusual. And it's really, again, we studied this through the phenomenon of water. And it's water that does this. I don't know what else is there, but water starts to order in these very chaotic spaces where you would get all kinds of, like whirlwinds, this, crazy like waterfall behavior. They start to organize. And we're still studying it. We don't understand how it works essentially, but we know that it does work, that water starts to organize itself in these chaotic spaces, and it forces everything else around it to order. So like when I said that example of dirt, what happens is that dirt is then basically put in a different part of the environment so that it is organized, and then the water is organized, and so everything is organized, and it shouldn't be that way, but it is. It's very bizarre. And again, we're studying it very in depth because I think it has a lot of implications for chemistry and physics. But, I looked at it, because of this unique environment we're in, as a way to describe how we could say, hey, chaos could lead, or at least, if the environment seems chaotic, it could lead to order if we have the high cooperativity. And that's the spaces that I see at the molecular level. These spaces are the high cooperativity because basically they force the system to say, how do we work together to, continue to be whatever we want to be? So I don't know if that answers your question, Gianni, but that's the best I could do for fifth grade level.
Yeah, it does. Great. Thank you. Okay, let's go to Professor Eliav.
Thank you very much, dear Lucian, for really great presentation. Well, I have a small question. We know how to measure entropy in a system, but can you please explain how to measure cooperativity? Is it some kind similar to the potential energy of interaction, whatever? How do you think? What can we do in this?
That's actually a powerful question, Professor. It's something that in my community, I can't take full credit for it. I have a colleague in my department here at State, Jim Martin, who has really pushed it hard. It's an idea where, scientists since, I guess, the 17th century all the way through have looked at gas states, like they've looked at non-condensed media. So the idea that things are in isolation. So all of our laws and theories in science seem to focus on individualized states, that there is, we look at a molecule and then we derive an equation. And if there's any, this doesn't work, they make some fudge factors. But what my colleague, who's a physical chemist, has said, hey, why don't we look at an ensemble? Look at all the molecules. They're all going to somehow make some contribution. And so I've been studying that. So the idea of cooperativity is, without getting too crazy, geeky, is like icing. Like you go from water, which is a disordered state, right? Everything, water molecules, to ice where they start to stack. And so we're looking at that. That's kind of the cooperativity that we're looking at, is that you've got an opportunity because of the way, say water looks like, for it to start to stack. And so we're studying how it stacks in these high entropy states, how it, because that's really our only handle right now, is how do we, look at how water stacks, and then how things in it, how they stack. And so that's what we're studying is, and you can look at that through, I guess, some sophisticated techniques like NMR or, light, seeing how these things sort of like X-ray crystallography, how they start to look together when they're, put together. So it's really a very strange kind of phenomenon, but because it doesn't really fit with what the 17th through 21st century physics chemistry says. So I think, and I give him credit. I think that if this continues to be a breakthrough, as I think it is, I told him, I told him at some point, I said, because of your work, which I really believe in, I think I can apply it to humanity. And, that was the proposal I sent to you, Ephraim.
Okay, next question is from Alex here in the Zoom. Go ahead, Alex.
Thank you for the very interesting presentation. I would like
Thank you
to
for the
ask in
perfect
the same
presentation. I'm
direction
going
as the
to
tribe.
ask within the same realm as Professor Eliav. I wanted to say we understand that entropy is basically chaos. If we consider elements which are interacting in a chaotic state, we can imagine that as a result they will achieve some structured interaction, some organized manner of cooperation. Is there any kind of modal system that could describe the transition? For example, there is Brown motion. We start to organize some systemic interaction between molecules and this Brown movement motion, and they converge into an organized system. Is there a modal that describes that, or is it just an idea?
No, it's beautiful. Thank you, Professor Averbach. So I have to give credit where it's due. There's a model called transition zone theory, which essentially encapsulates that. If you want to look it up, again, it's Dr. Martin. As you said, in Brownian motion, the idea is that you've got, a lot of colloidal, system. You have a colloidal system where everything is, all over the place, right? And as you impose some stress on it, like through the environment, what happens is things start to sense. And I don't like that word too much at the molecular level because it's very strange, but the molecules recognize where they are. So as you start to compress it, as you start to force it to come together, they start to organize in ways in this chaos, right? Because they're forced to get together in ways that leads to the minimization of stress or energy. It's very, very interesting. So this transition zone theory is very beautiful in showing how you can now get new assemblies that are ordered from the chaos. It's very, very, very strange. And again, I think in physics, it offers a new insight into understanding the power of entropy as an organizing force, which is not like Gianni said, it's not something you would go, oh, that makes sense. But, what we've studied with water, yeah, it's working. But you have to invoke cooperativity, the idea that every molecule in that state is important. It's just not a few at the front, at the interface or that are active. It's every molecule has a role, which to me is a very beautiful thing. It's a very beautiful thing.
Excellent. Thank you, Professor Lucia. We're going to move on. Sorry we couldn't get to all the questions. And we said in the beginning that we're in an